for linear programming, we're going to take that same concept from what we just got through covering in 7.5. That is, trying to find what's called this feasible region, that cross-section solution, that region of the cross sections. Once we find that, to be able to maximize what's called a constraint equation, what we're going to do is just find all the boundary points, the corner points of the region, and then put those boundary points into the so-called constraint equation to see what's the maximum, what's the minimum. Now that's just the math behind it, but let's look at just a real life problem to see how this concept has come about. Here's an example of a linear programming type problem that we will be solving in this section. This is what we call a modeling problem. A modeling problem just models or mimics just something in the real world. We can use mathematics to aid in solving these modeling problems. Now, if you notice that what's here is exactly what we just dealt with in the previous section. All they added was this constraint equation. So basically what they're saying is, if I can take this system here, if we can solve it, that is find that cross section, then what points on that system maximizes Z? What's the biggest value for Z on the so-called here, the constraints? No problem. Let's look at where this problem actually came from. So here's an example. Bottled water and medical supplies are to be shipped to survivors of an earthquake by plane. Each container of bottled water will serve 10 people, and each medical kit will aid 6 people. So here we get this constraint or restraint, this Z equation, that Z is equal to 10 times X plus 6Y, where the 10 represents each container serving 10 people, and then each medical kit can serve 6. So here, the water bottles represent the X, and then the Y represents the medical kits. Okay. This was an actual situation that occurred. So in this humanitarian relief effort, each plane can carry no more than 80,000 pounds. So that's the max. That's how we get this number here. The bottled water weighs 20 pounds. Remember that X represents the bottled waters. And then each medical kit weighs 10 pounds. So their goal is, how many supplies can we get on this plane to carry it to their destination? So the medical kits represents Y. So you can see how we build this inequality. It has to be less than or equal to, because we can't go above the weight limit for the plane. And so now each plane can carry a total volume of supplies that does not exceed 6,000 cubic feet. So the number of bottled waters, that total volume with the total volume of the medical kits X plus Y has to be less than or equal to 6,000. So you see here how we can model, and we get this X plus Y less than or equal to 6,000. And so then from there we get this problem. Now I show you that because in the real world, and that's basically where you're headed in terms of, you know, what are we doing in college, and how is this going to help me do such and such. Well, here's the thing. Math is so important everywhere. And you want to be able to see how we can apply mathematics. We call it modeling or modeling problems, and they're everywhere. Economics, political science, posters, in terms of supply, demand, supply chain, production, all of that, they're all based on modeling, and modeling simply means here's a real world situation. Can we put some math to that, and then solve the math and let the math help us in what we're actually trying to do. So the objective function is to be able to here maximize z, this z equal to 10x plus 6y, based on those constraints. Well, here is the method in terms of solving. We're going to graph the system of inequalities representing the constraints. That's what we did back in the previous section. Okay. And then number 2, find the value of the objective function at each corner or vertex. That means for that region that you end up with the solution, that cross section, take all those vertexes, those boundary points, and then put those values into z, because this objective function is z. And then whichever number gives you the biggest, that's your max. Whichever number gives you the smallest, that's your minimum. If they ask for the maximum, then you purport the largest value. If they ask for the minimum, you purport the smallest value. Here's the problem here in terms of this humanitarian relief effort, and here's how they solve that. Once they got that cross region, the region that was the feasible solution, which is here, then you look at all of the boundary points. You take these points, some x, some y, and you're going to plug them into this guy right here for x and for y. Whichever value is the largest, that's your max. Oh, here's where they do that. They take all those corner points for x and y, plug them into z, and then they're looking for the max. So they know that the maximum weight for that plane cannot exceed over 80,000. To make that happen, then they can have no more than 2,000 bottle crates of water, and then 4,000 crates for the medical kits. Okay. And this is right in the book. Matter of fact, I use the ebook, so if you don't have the book, you just have just my math lab. You just click on e-text, and the book content is there. And I thought that was a pretty good illustration of what we're doing. Now here's the problem. Here's a problem for us. How about that? So an objective function, that objective function is called z. Excuse me if I had referred to it as the constraint. The constraints are this system of inequalities. So what we're going to do is, in my math lab, it says complete parts A, B, and C. So what is that? I think the first one is like you graph it. So let's go ahead and just graph this guy. I didn't put my graph up there. Huh. That's fine. So this is x greater than or equal to 0. So x greater than or equal to 0 is a vertical line. I find x equals 0 and then just draw a straight line. Well, that's going to be the y-axis. So this is automatically the y-axis. And y equal to 0 is the x-axis. Well, it's going to be more than that since it's an inequality, but that's where we start. So here I have this this x equals 0, and then it says everything bigger than that. So that's going to be all of this. And then for y equal to 0, that's the x-axis. Can't see that, but you'll see when I do everything above it. Y greater than, that's everything above it. So you see the cross-section is just the first quadrant, right? Just the xy plane. So we got those two out the way. So let's look at this guy. This is y is less than or equal to negative 3x plus 12. And then here, this is y greater than or equal to negative x plus 4. Okay. So when we look at this inequality, let's graph it. The y-intercept is 12. I'm going to just say it's here. And then the slope is go down 3, go over to the right 1. Say something like that. And that's less than. So for right now, I'm in this triangle right there. Let's look at the last one. The y-intercept is 4. The slope is negative 1 over 1, go down 1, go over to the right 1. And that guy is everything above it. All right. It's real sweet in my math lab because it gets all the straight lines and it's very accurate, for you. But I have, look at the points, the corner points. One there, one here, and one here. Now, the real cool thing in my math lab, you'll be able to see those points on the graph. And so you don't have to kind of worry about the math in terms of, finding them. So my graph is off because of my graphing. Let's see. 4. Yeah, this guy goes over a little bit more like that. Didn't mean to get rid of that one. When you pick those points in my math lab, it will give you the exact graph. And so I'm, none of what I'm doing here is by scale, because I just picked up and said, okay, this is 12 up here, this is 4. But I didn't scale it off to say, okay, this is 1 unit, 2 units, 3 units, and nothing was proportionate. So when I did that in my math lab, it gives you the exact graph. And so that's the region in there. Here are the points, 1, 2, it's just 3. Once you get the graph, you'll get the exact graph in my math lab. Now you can look at those points. So here, This point here is x is 0, y is 12. This point here is x is 0, y is 4. And this point here is x is 4, y is 0. Okay. Now the so-called hard math is where we have to just take the equations, set them equal to each other, and then solve for x and y for each point. That's typically what we do. But the real neat thing is that we got the graph tool in my math lab. Let's just use that to our advantage. And so it's giving us the points. So what we do is we take each point, 0, 4, right? We're going to plug them into z. See what value do we get. Take the next point, 0, 12, plug that into z. I get 60. 4, 0, plug that into z. I get 12. So the biggest guy, the biggest value is 60. So these constraints are said to be maximized if they are looking for the maximum. Sometimes they look for the minimum, and then you would put in 4, 0 on the value for 12. But here, I think they're trying to maximize, so it's going to be 0, 12, and 60. It says, part B, find the value of the objective function at each corner of the graph region. Let's go back. So all they're saying is these values here for z. It's not a highlighter. 60, 20, 60, and 12. And then part C, it says use the values in part B to determine the maximum. So you're going to go back over to, when you do your chart over here, which one gave you the max. Well, the max was at 60 from values x is 0 and y is 12. Just plug that information in there, and that's the problem. Okay. Okay, so what I'm going to do now is I'm going to open up my math lab, if I remember my password, and look at one of those problems just to make sure that that we can kind of all do it together.